All right, let's dive right into this explainer on series circuits, or as we like to call it, the train. Today we're going to demystify the flow of electricity in a series circuit using a brilliantly simple analogy. We're taking concepts that can honestly feel a bit abstract and invisible, and we're anchoring them into something incredibly intuitive. So what actually happens to the electricity in your device when you add another battery? It's a pretty fundamental question of basic electronics. Whether you're tossing batteries into a flashlight or looking at the massive battery banks in an EV, you're interacting with these principles. And today, we're going to see exactly how changing out components impacts that invisible flow of electrical current. Well, to really get a grip on a series circuit, we need to picture something way larger than just copper wires and tiny batteries. Imagine the electrons flowing through the wires are actually the connected cars of a massive cargo train winding along a single continuous track. There are no alternate routes here, no sidetracks, just one single path forward. The core idea here is that you can think of the electrons in a series circuit exactly like a train. Because all those cars are physically hitched together, the back of the train literally cannot go any faster than the front. It's a completely interdependent system. As soon as one part moves, the whole shebang moves together at the exact same time. The electrons in your circuit behave in that exact same coordinated way. And that brings us to a huge takeaway. Current is the exact same everywhere in a series circuit. Those electrons are flowing at the exact same speed in all the wires. This means you could hook up an ammeter, the tool we use to measure current, at literally any position in the loop, and it will give you the exact same result. The flow isn't faster near the battery or slower near the end. It's completely uniform throughout. Section 1. Powering up with cells or adding more engines. In our circuit, the engine is the cell. Think of a cell as a chemical powerhouse. It's simply a store of chemical energy that changes into electrical energy. So adding more cells to your circuit means you've got more stored chemical energy available to convert. You are effectively adding more engines to the track, directly boosting the pushing power behind our electron train. When you compare a standard circuit with a single cell to one that has two cells in series, you can really see how this builds. Because of that second cell, the upgraded circuit has exactly double the electrical energy available to push those electrons along the track. And because we doubled the energy, the current literally doubles right along with it. A single cell circuit pushes a current of 1.4 amps, but add that second cell, and boom, it jumps to 2.8 amps. In the real world, this surge of faster-moving electrons means your connected lamp is going to shine significantly brighter. Section 2. Slowing down with lamps or adding heavy cargo. In this analogy, lamps are our cargo. Now, lamps aren't just passive light sources. They actively require and transfer energy, changing electrical energy into light and thermal energy. Because they do this, they act like a heavy load on the track, which forcefully slows the electrons down as they move around the circuit. By transitioning from a circuit with just one lamp to one with two lamps in a row, while keeping the power source exactly the same, we're demanding twice as much energy transfer. We've added more resistance. We are basically weighing down our train with extra freight. Since the electrons are now dragging that extra cargo, they're forced to move at half the speed. Our ammeter reading gets slashed in half, dropping from that original 1.4 amps straight down to 0.7 amps. And with less current flowing through, those lamps are going to look noticeably dimmer than before. It really is a beautiful balancing act. It's a constant push and pull. Adding cells gives you more engines, making things brighter and faster. Adding lamps gives you more cargo, making things dimmer and slower. But remember, no matter how fast or slow that train is moving, the current always remains totally uniform throughout the entire track. Section 3. The 1870s electricity bill and paying for electricity. To see why understanding this energy draw actually matters in the real world, let's step back in time for a second. How did you actually pay for electricity in 1870? Today, it's super easy, right? You get a bill based on exactly how many kilowatts you used. But back when cities were getting their very first municipal grids, there was a huge practical problem. There was absolutely no technology available to measure the actual quantity of electricity a home was using. Since they couldn't just meter the current flowing into a house like they did with water, early utility companies had to get a little creative. They understood the physics we just talked about, that each lamp acts as a specific load on the system, so they relied on what was called the pay-per-lamp method. This meant people paid strictly based on the physical number of components acting as a load on the grid. Literally, 4 lamps equal double the bill of 2 lamps. So if you had 4 of those antique electric lamps sitting in your parlor, you paid exactly double what your neighbor with 2 lamps paid. And get this, that was regardless of how often you actually switched them on. All right, before we wrap up this explainer, let's lock in these core rules. A series circuit is an all-or-nothing system. Current acts just like a single connected train. Adding cells, our engines, increases the current. Adding lamps, the cargo, decreases the current. And through it all, the speed remains constant at every single point in the loop. So, I'm going to leave you with this final puzzle to test your new physics knowledge. If you add 1 battery and 1 lamp to your circuit at the exact same time, does the current go up, down, or stay the same? Think about our train, balance the engines against the cargo, and keep exploring.